Okay, welcome to the classroom. Today we're going to have a look at the third lesson in chapter 8. There are two topics. First one is the motion of charged particles in magnetic fields. And then we'll have a look at applications of electric and magnetic fields. So atoms and molecules are particles that are the building blocks of our universe. How do scientists study the nature of these small particles? The mass spectrometer, shown here in figure 1, is an instrument scientists use to study atoms and molecules. Mass spectrometers are used to define the elemental composition of a sample or molecule, to determine masses of particles, and to reveal the chemical structures of molecules. So how does a mass spectrometer work? Imagine a billiards table with a billiard ball rolling across the table from your left to your right. If you hit the ball with a sideways force, the ball will move away from you, right? Now suppose the bowling ball rolls across the table in the same direction. If you apply the same sideways force on the bowling ball, it will also move away from you, but not as far. The masses of the billiard ball and bowling ball determine the distance they will be deflected by the force. If you know the amount of force, the speed of the balls, and the curve of their path, you can calculate the mass of each ball. The less deflection there is, the heavier the ball must be. In a similar way, a mass spectrometer uses the magnetic force to deflect electronically charged particles. Atoms are converted into ions and then accelerated into a finely focused beam. Different ions are then deflected by the magnetic force by different amounts, depending on the mass of the ion and its charge. Lighter ions are deflected more than heavier ones. Ions with more positive charge are deflected more than ions with fewer positive charges. Only some ions make it all the way through the machine to the ion detector, where they are detected electronically. If you vary the magnetic field, different types of ions will reach the detector. So scientists use the mass spectrometer to identify unknown compounds, to determine the structure of a compound, and to understand the isotopic makeup of molecular elements. The mass spectrometer has applications in the medical field, the food industry, genetics, carbon dating, forensics, and space exploration. Okay, so now let's have a look at charges and uniform circular motion. To understand how a mass spectrometer works, we first need to understand how a directional force affects the motion of an object. In this case, a charged particle. Okay, consider the direction of a magnetic force, Fm, and how this force affects the motion of a charged particle. We know that Fm, the magnitude of the magnetic force, should equal QVB sine theta, right? For simplicity, we can assume the magnetic field B is uniform. So the magnitude and direction of B are the same everywhere. So as shown here in figure 2a, there's a charged particle, positive Q, moving at velocity V, parallel to the direction of B. In this case, the angle theta between V and B is 0. The factor sine theta in this formula, Fm equals QVB sine theta, is also 0, right? So in this case, because the angle theta between V and B is 0, the magnetic force in this case is also 0. If a charged particle has a velocity parallel to the magnetic field B, then the magnetic force on the particle is 0. On the other hand, as it shows here in figure 2b, there's a charged particle moving perpendicular to the magnetic field B. Now we have theta equals 90 degrees. In this case, we know sine 90 degrees or sine theta equals 1, right? Then the magnetic field, the magnitude of the magnetic force is given by Fm equals QVB. And the force is perpendicular to the velocity. You can check this by using the right-hand rule, right? Recall that when a particle experiences a force of constant magnitude perpendicular to its velocity, the result is circular motion, right? We have already studied this in the very first unit, which is shown here in figure 2b. Hence, if a charged particle is moving perpendicular to a uniform magnetic field, the particle will move in a circle. This circle lies in the plane, perpendicular to the field line. Which is shown here in figure 2b, right? The radius of the circle can be determined from Newton's second law and centripetal acceleration. Also recall that for a particle to move in a circle of radius r, there must be a force of magnitude mv squared over r directed towards the center of the circle. Here, the force producing circular motion is the magnetic force. Then we have the magnetic force, Fm, equals the centripetal force, which is mv squared over r, right? Is the relationship here. The magnetic force is perpendicular to velocity and sine 90 degrees equals 1. So we can insert Fm equals QVB, which is here, into this equation. Thus gives us QVB equals mv squared over r. So we can solve for r, which gives us r equals mv over qb. Now calculate the value of r for an electron that has a speed of 5.5. For example, consider this example here. This is an example. If we have an electron that has a speed of 5.5 times 10 to the power of 6 meters per second, moving in a magnetic field of strength 5 times 10 to the -4 teslas. Inserting these values into the equation, r equals mv over qb. And also, be careful with the units here. You should use old SI units. We can get the radius is actually here. Radius of the circular motion is 6.3 times 10 to the power of -2 meters. So this calculation shows that we can determine the radius of particle's deflection if we know the mass of the particle, its velocity, and its charge, together with the strength of the magnetic field through which it moves, right? Okay, so I'll give you some time to have a look at these figures. Make sure you understand the principles here, okay? All right, next, let's have a look at a sample problem. So here we have an electron starts from rest, a horizontally directed electric field accelerates the electron through a potential difference of 37 volts. The electron then leaves electric field and moves into a magnetic field. The magnetic field strength is 0.26 teslas. Directed into the page, which is shown here in figure 3. And the mass of the electron is also given, which is 9.11 times 10 to negative 31 kilograms. There are 3 questions you need to answer. First, can you determine the speed of the electron at the moment it enters the magnetic field? Then determine the magnetic field, determine the magnitude and direction of the magnetic force on the electron. Then determine the radius of the electron's circular path. Okay, here I'll give you 5 minutes to have a look at these 3 questions. And after that, we'll have a look at the solution together. You can start now. Okay, then let's have a look at the solutions together. Okay, first question, we know the decrease in the electrons electric potential energy equals the increase in its kinetic energy, right? Which means negative delta EE equals delta EK, where negative delta EE is Q delta V, and EK equals 1/2 times M times V squared. So the speed of the electron before it enters the electric field. Also note that the speed of the electron before it enters the electric field is 0. Therefore, we know Vi equals the square root of 2Q delta V over M, right? So put all the values in. We have the initial speed, Vi equals 3.605 times 10 to the power of 6 meters per second. So the initial speed of the electron at the moment it enters the magnetic field is about 3.6 times 10 to the power of 6 meters per second. Any questions? Okay, next, let's have a look at the magnitude and direction of the magnetic force on the electron. So we can use Fm equals QVB sine theta to determine the magnitude of the force. This gives us approximately 1.5 times 10 to the negative 13 newtons. Then we can apply the right-hand rule for an electric charge moving through a magnetic field. We can point the fingers of the right hand in the direction of the external magnetic field into the page. And then point the right thumb in the direction that the charge is moving to the right. Then the palm points in the direction of magnetic force for a positive charge up the page, right? Because the charge is negative, so the magnetic force is down the page. So we can make this statement here. The magnitude of the magnetic force on the electron is about 1.5 times 10 to negative 13 newtons, and direction should be down the page. Any questions? Okay, next. The only force acting on the electron is a magnetic force, right? So this force is perpendicular to the electron's velocity, causing it to move in uniform circular motion. So we know the magnetic force is a centripetal force. So we have Fc equals M, because Fc equals mv squared over r, and on the other hand, we know Fm equals qvb. Therefore, we have qvb equals mv squared over r. And in this way, we can solve the radius of the motion r equals approximately 7.9 times 10 to negative 5 meters. That's the radius of the electron circular path. Any questions? Okay, if no questions, let's consider another problem. Okay, here a researcher using a mass spectrometer observes a particle traveling at about 1.6 times 10 to the power 6 meters per second in a circular path of radius 8.2 centimeters. The spectrometer's magnetic field is perpendicular to the particle's path and has a magnitude of 0.41 teslas. First, calculate the mass to charge ratio of the particle. Second, can you identify the type of particle using table 1 according to your calculation in the previous question? Okay, again, I'll give you 5 minutes to consider this question by yourself. You can start now. All right, now let's have a look at the solution together. So again, similar to previous problem, the only force acting on the electron is a magnetic force, whose magnitude is given by QVB sine theta. This force is perpendicular to the electron's velocity, causing it to move in uniform circular motion. The magnetic force is the centripetal force, Fc, which is mv squared over r, right? So we have QVB equals mv squared over r. In this way, we can find the mass to charge ratio, m over q equals rb over v. So put all the values in, we have m over q is approximately 2.1 times 10 to negative 8 kilograms per coulomb. So the mass to charge ratio of particle is about 2.1 times 10 to negative 8 kilograms per coulomb. And according to table 1, we know this particle is the isotope deuterium. Any questions? No? Okay, then let's consider another question before we move to the next topic. So here a researcher uses a mass spectrometer in carbon dating experiment, which is shown in figure 4. The incoming ions are a mixture of carbon 12 plus and carbon 14 plus. And they have speed v equals 1.0 times 10 to power 5 meters per second. The strength of the magnetic field is 0.10 teslas. The mass of the electron is 9.11 times 10 to negative 31 kilograms. The mass of the proton and the mass of the neutron are both 1.67 times 10 to negative 27 kilograms. The researcher first positions the ion detector to determine the value of R for carbon 12 and then moves it to determine the value of R for carbon 14 ions. How far must the detector move between detecting carbon 12 ions and carbon 14 ions? Okay, I'll give you 5 minutes to consider this question, and then we'll have a look at the solution together. All right, let's have a look at the solution together. So the ion detector must move a distance equal to the difference in the diameters of the circular trajectories, right? So first of all, we need to find the radius of the circular motions of the two particles. Okay, first we can determine the mass of each isotope. The mass of carbon-12 equals 6 of the mass of protons plus 6 of the mass of neutrons plus 5 of the mass of electrons, right? And this gives us about 2.004 times 10 to negative 26 kilograms. We use the same method, we can find the mass of the C14 equals about 2.338 times 10 to the power of negative 26 kilograms. Then if we know the masses of the two isotopes, we can calculate the radius of the curvature of each particle. We can use R equals mv over qb. First of all, the radius of the motion of the carbon-12 equals 0.1252 meters. And then use the same method, we can find the radius of the carbon-14, which is 0.1461 meters. Then delta D should equal twice of the difference between the two radius, which is approximately 0.04 meters. So the ion detector must move a distance of 0.04 meters. Okay, so have a look at this solution here. Any questions, just let me know. All right, if you don't have any questions, let's have a look at the next topic, which is Earth's magnetic field. So charged particles traveling parallel to a magnetic field do not experience a magnetic force and continue moving along the field direction, right? Charged particles traveling perpendicular to a magnetic field experience a force that keeps them moving in a circular path. Charged particles with velocity components that are both parallel and perpendicular to a magnetic field can experience a combination of these effects. The result is a spiral path that resembles the shape of a coil of a wire. The particle travels with a looping motion along the direction of the field, which is shown in figure 6 here. So charged particles entering Earth's magnetic field are deflected in this way. Since they are charged particles with a component of the velocity perpendicular to the magnetic field, they will spiral along the field lines towards the magnetic poles. This motion results in a concentration of charged particles at Earth's north and south magnetic poles, which is shown here in figure 7 on the top right. The collisions between the charged particles and items in the atmosphere release light that causes the glow of the aurora. In the northern and southern hemisphere. At high altitudes in Earth's magnetic fields are zones of highly energetic charged particles called the Van Allen radiation belts. James A. Van Allen, an American physicist, discovered the toroidal zones of intense radiation while studying data from a satellite he built in 1958. Van Allen was able to show that charged particles from cosmic rays were trapped in Earth's magnetic field. Most intense over the equator, the belts are almost absent over Earth's poles and consist of an inner region and an outer region, which is shown here in figure 9. The outer belt contains charged particles from the atmosphere and the sun, mostly ions from the solar wind. The inner one, Allen belt, is a ring of highly energetic protons. The concentration of charged particles and radiation can easily damage electronic equipment. So researchers programmed the paths and trajectories of satellites and spacecraft to avoid these belts. Okay, next, let's have a look at the concept of field theory. We associate the term force with the physical action of one object on another. When we talk about the force of a bat against a baseball, our minds use a concept of contact between the objects, which transmits the force. To develop a more accurate concept of force, we need to talk about it in terms of fields. We know that all objects are made of atoms interacting without actually touching each other. There are spatial gaps between the atoms in the bat and the baseball. So the idea that the bat makes contact with the ball is deceptive. In reality, electromagnetic forces affect the interacting items in each object. So how do we create an understanding of the gravitational, electric, and magnetic forces? We need a scientific model that describes different types of forces that exist at different points in space. And field theory does that. Field theory is a scientific model that describes forces in terms of entities called fields that exist at every point in space. The general idea of fields likes different kinds of forces once thought of as separate. Field theory states that if an object experiences a specific type of force over a continuous range of positions in an area, then the field exists in that area. Field theory can be applied in explaining the minute interactions of subatomic particles, as well as describing motions of galaxies throughout the universe. So studying gravitational, electrical, and magnetic forces has revealed differences and similarities between these forces and their responsive fields. The electric and magnetic fields have a stronger effect on the motion of subatomic particles, such as protons and electrons. but the gravitational field has a stronger effect on large objects, such as planets, galaxies, and clusters of galaxies, which is shown here in figure 10. So in a summary, the field theory is just a scientific model that describes forces in terms of entities that exist at every point in space, right? So the electric and gravitational forces resemble each other in that the force on an object depends on the location of the object. The magnetic force, however, depends on a charged object's motion. The direction of electric and gravitational forces points from the object towards the charge or mass source. The direction of the magnetic force depends on the motion of the charged particles with respect to the magnetic fields. Despite these similarities and differences, field theory states that electric and magnetic fields are more closely related to one another than they are to the gravitational field. In fact, the electric and magnetic fields are thought to be different aspects of a single field, the electromagnetic field. They are used in conjunction with one another in a multitude of innovative technologies ranging from particle accelerators to artificial hearts. Okay, so that concludes our first part of today's lesson. You can then take a 10 minutes break, and after that, we'll have a look at the second part of this lesson. We'll describe some applications of electric and magnetic fields. Okay, next, let's have a look at section 8.5. We'll briefly talk about applications of electric and magnetic fields. If you have a pet dog or a cat, you probably have tags on it that gives information on how to contact you if your pet ever get lost. Unfortunately, these tags can fall off. A more secure way to identify or ID your pet is to have your veterinarian implant an ID microchip under the skin. The microchip stores information electronically and can be read by a scanner. Microchips have many uses. Credit card companies and banks use them to help prevent theft of account information and fraud. Microchips are more secure than magnetic stripes, less easily damaged, and very convenient. With contact-based chip cards, which are read using a magnetic field, you do not even have to swipe or insert your card. You just wave the card over the microchip reader. These advances in technology are due to our understanding of fields. Okay, so first let's have a look at the RFID chips. The radio frequency identification technology, or RFID, is a tracking technology that uses microchips less than a millimeter in size, which is shown here in figure 1. So microchips act as transmitters and responders to communicate data by radio waves. This technology uses electromagnetic waves, which are a combination of electric and magnetic fields. The tag detects a specific radio signal sent by an RFID reader. When the transponder receives the radio signal, it then transmits a unique numerical identification code back to the transceiver. Every tag is encoded with a unique set of numbers for the purpose of identifying and tracking items. RFID was invented in 1969, but has only recently become widely available in commercial applications. RFID tags have uses in product tracking, transportation, and logistics, animals and plants identification, and payment systems. RFID tags have many technological advantages over barcodes. RFID tags can be read inside the container and through materials such as water and body tissue. They can be embedded into any item not made of metal. They are used in wooden shipping pallets, plastic key fobs, hotel keys, credit cards, gas cards, and driver's licenses, while barcodes can only be read one at a time. Hundreds of RFID tags can be read simultaneously. Imagine if all the items in a store were enabled with RFID tags. When you push your card through the checkout scanner, the RFID reader and tags could instantly calculate prices of all the items in your cart, which is shown here in figure 2. Here, a shopping cart equipped with an RFID scanner and display. Okay, next application is the MR fluid dampers. Can you imagine constructing a building with a material that changes from a solid to a liquid and back to solid again? Architects and engineers have long known that for a structure to withstand the seismic waves of an earthquake, the structure must be flexible, not rigid. The MR fluid is a material that can change state from solid to liquid and back to solid again using a magnetic field, which is shown here in figure 3. Although the MR fluids may seem like an idea from a science fiction novel, they are now being used in the construction materials of buildings in earthquake-prone regions. Under normal conditions, an MR fluid is solid, but it changes to a liquid in response to sensors placed in strategic locations that control a magnetic field during an earthquake. This semi-liquid state of certain building components allow a building to absorb shock waves and reduces potential damage. Buildings constructed with MR fluids are called smart structures. The liquid portion of MR fluid material is usually a type of high viscosity or thick oil that keeps small iron particles suspended in it. The iron particles are the key to changing the fluid into a solid and vice versa. When a magnetic field is activated near the MR fluid, the fluid greatly increases its viscosity. Although MR fluid was introduced in the 1940s, the technology required to control the force of the magnetic field and thus the strength of the fluid is a recent development. Due to advancements in the technology, MR fluids are now being used in car shock absorbers, washing machines, and exercise equipment, and so on. Okay, next, let's have a look at the high voltage power lines. Every day, we come into contact with invisible lines of force from electrical and magnetic fields. They surround any transmission or use of electricity, from high voltage transmission and power lines to the wiring and lighting in our homes. Electromagnetic fields are also found near household appliances, electric equipment such as cell phones, and electric motors. In the 1980s, people began to worry that exposure to the intense electromagnetic fields around the high voltage wires posed serious health risks. Some early studies showed a link between a magnetic field strength and an increased risk of cancer. People, particularly young children, living under or near large high voltage transformers were brought to be at high risk for developing illnesses. Since that time, however, scientists from Health Canada, the Federal Provincial Terrestrial Radiation Protection Committee, or FPTRPC, and the U.S. National Institute of Environmental Health Sciences have independently reviewed over 2 decades of research involving adults and children exposed to electric and magnetic fields. To date, they have not found clear evidence linking high exposures with the adult cancers studied, such as breast cancer, brain cancer, and so on. In addition, they concluded that the studies showed only a weak association between exposure to electric and magnetic fields and childhood leukemia. The case is not closed, however. Studies involving electromagnetic fields are difficult to perform because they are not controlled investigations. In a controlled investigation, scientists can manipulate one variable and see the outcome on a responding variable while keeping all other conditions constant. Studies related to exposure to electromagnetic fields are often correlational. A correlational study looks for relationships or patterns between measured variables and may depend on many variables affecting the outcome. Sometimes a correlation is weak, but is still reported as a result. For example, a neighborhood may have a high incidence of cancer and be located next to a high voltage line. A result may be reported saying that high voltage lines have been linked to cancer. However, the neighborhood may also be located near a factory that emits a carcinogenic pollutant. The difficulty for scientists is to determine what causes the effect. Was it the factory, the high voltage lines, or both, or neither? It is always important to consider type of study when interpreting the conclusions. All right, next let's have a look at the medical applications. Water composed of hydrogen and oxygen atoms is a part of all cells. The human body is approximately 2/3 water by mass and contains billions of hydrogen atoms. In a magnetic resonance imaging or MRI device, magnetic fields interact with these hydrogen atoms, producing images that doctors can use to diagnose injuries and disease. The MRI uses a superconducting magnet to create a large, stable magnetic field of approximately 2.0 teslas. The large magnetic field is needed to produce precise images of the soft tissues inside the human body. For an MRI machine to obtain images, a patient must lie on a movable bed that slides into a tube in the center of a magnetic field. Hydrogen atoms in the body can behave like atomic-sized compasses, whose north and south poles normally point in random, changing directions. When the body enters a magnetic field, the body's hydrogen atoms align their poles either in the direction of the field or opposite to the direction of the field. The number of atoms aligned with the field will almost equal the number aligned opposite, but there will be a small difference in the numbers, which is about half in a million. This difference in the number of items aligned versus anti-aligned depends on the particular material that the items are part of, such as skin, bone, or organs, and whether the material is normal and healthy. or abnormal and diseased. Next, the radio frequency pulse is directed towards the area of the body to be examined. The pulse will cause the anti-aligned items to spin and align with the magnetic field. When the pulse ends, these items spin around again, but emit energy they absorbed from the pulse. The MRI device sends a regularly repeating radio frequency pulse, which causes items to emit a regular energy signal that can be detected by receivers. While this is happening, these gradient magnets are activated, quickly turning on and off in a particular pattern. The gradient magnets are much smaller than the primary magnet, but they allow for precise alteration of the magnetic field. By altering the gradient magnets, the magnetic field can be specifically focused on selected parts of the body. The MRI device then signals information to a computer, which converts the data into an image, which is shown here in figure 4. Manipulating the gradient magnets in the MRI allows doctors to obtain three-dimensional pictures of specific body areas without moving the patient body. Okay, so these are the applications of the electromagnetic fields. And that concludes our discussion in today's lesson. Okay, I'll see you next time.